everyone. The paper we will discuss today is the IFMIF-DONES project, Preliminary Engineering Design. Chapter 2.2 Reliability, Availability, Maintainability, and Inspectability RAMI. IFMIF-DONES is conceived as an irradiation facility with the final objective of producing the material database in due time according to demo needs. In that sense, IFMIF-DONES will be a damaged DPA production facility with a very demanding operation schedule. Therefore, proper performance in terms of reliability and availability is essential for the IFMIF-DONES mission. As a user facility, IFMIF-DONES is designed to be flexible, and the final performances will depend also on the definition of the radiation program. Moreover, the availability needs of IFMIF-DONES are fully linked to the fusion roadmap and may vary according to the definition of the fusion program. In particular, the facility has to be designed for high availability, and 70% over the calendar year is established as the horizon requirement for its engineering design. This requirement is established for the normal operation phase, and no specific requirements have been established for other different possible phases of IFMIF-DONES. Assuming a conservative approach, this availability goal is translated into a maximum inherent availability requirement of 70% over the scheduled operation time. This imposes higher inherent availability requirements on the different IFMIF-DONES systems, such as 87% for the accelerator systems, 94% for the lithium systems, 96% for the test systems, 98% for the plant systems, and 98% for the central control systems, based on the results obtained in IFMIF-RAMI studies. The plant will operate on the basis of a 24 hours per day, 7 days per week cycle, regardless of the detailed operation schedule. Several principles can already be assumed. The DONES operation schedule will be determined taking into account that it is part of the fusion roadmap, being directly coupled to the demo schedule. A minimum operational life irradiation of 20 years is assumed. Irradiation periods are limited by mechanical properties, degradation in materials used in irradiation modules, and target assembly and the maintenance scenario. The IFMIF-DONES operation schedule will be created according to these constraints. A basic assumption of the maintenance strategy of the IFMIF-DONES plant is that the materials irradiated in a given period of time will not be required to be re-irradiated. The reference maintenance scheme is based on a yearly cycle with two scheduled maintenance periods, one short and one long preventive maintenance period. The long maintenance period, 20 days, will be devoted to general maintenance of IFMIF-DONES, mainly for maintenance in the lithium systems and test systems, and for long-term accelerator maintenance. The short-term maintenance period, 3 days, will be devoted to activities in the accelerator and other ancillary and conventional systems. This maintenance period includes also the replacement of ceramic discs of the ion source. The RAMI studies being conducted on the lithium and test systems have identified as the main sources of uncertainties the assumptions taken on the lifetime of the systems under analysis. Maintenance strategy, failure rates, database, lithium loop process, boundary main electromagnetic pump, electromagnetic flow meter, impurity control system, and regulated operating mode assumptions. In the case of the accelerator and plant systems, the main sources of uncertainties are failure rates, the ventilation and decontamination systems, loss of power supply events, human factors, erratic alarms, fire, and other external hazards. Chapter 2.3 Logistics and Remote Maintenance. The DONES project consists of complete, complex, and heavy systems and components that need to be assembled and maintained on site. For several of these systems and components, it is required to perform maintenance, inspection, and monitoring tasks over many years in a hostile environment and in efficient, safe, and reliable manner. A systematic evaluation of the radiation and contamination environment in the different rooms and operational states has been developed in order to identify which activities will require remote handling (RH) during the maintenance tasks. DONES requires the use of advanced RH technologies to prevent human exposure to the high radiological activated environment and accomplish the stringent requirement as to plant availability based on the data available today coming from the engineering design, simulation activities, and the validation of some of the RH maintenance tasks to be reformed. It is possible to say that both objectives can be achieved. In fact, the RH procedures implemented and the correspondent operation can be completed remotely within the time frame allocated for the preventive maintenance of components. However, there are still experimental activities to be done to validate it and prove the suitability of the overall RH procedures and the equipment developed. Three main areas have been identified for the RH maintenance activities to be performed: the access cell, the lithium loop, and the beam dump area. Almost all RH maintenance activities for the IFMIF-DONES components will be performed in the AC, in fact. Critical components requiring RH are located inside of the test cell and in the target interface room, such as the HFDM, the TA, and ancillary systems such as pipes, plugs, connectors, instrumentation, cooling system, supporting structures, and so on. An overview of the AC is given in Figure 9. The AC is located just above the TC and above the room that houses the last component of the accelerator beam line TIR room. It is designed to accommodate all the RH equipment and tools to be used during the RH maintenance tasks and is sized to temporarily store all removable components, such as the test cell overplate and the 2TC top shielding, plus plugs USB and LSP while the TC is open, as well as for the shielding plugs on the AC floor that connect to the rooms in the lower floor. The main operations to be performed in this area are opening and closing of the TC, including plugging, unplugging of electrical and cooling pipes connections, HFTM exchange and its transportation to the irradiating waste treatment cell for storage or dismantling, TA exchange and its transportation to the irradiating waste treatment cell for storage or dismantling, TIR components, replacements such as vacuum plugs, bulbs below, collimator, and diagnostics. In addition, as an exception, RH operations on other components could be required, such as the exchange of the following. In addition, as an exception, RH operations on other components could be required, such as the exchange of the following: interface shielding plugs, ISP for the lithium inlet and outlet pipes, steel liner of the TC, cooled walls of the TC, the 5PC piece TA support structure, quench tank, the main RH equipment located in the AC are two heavy rope overhead cranes, HROCs, one in top of the area where the TC is located and another one on top of the area where the last components of the accelerator line are located. These are nuclear-grade multiple rope double beam overhead traveling cranes dedicated to performing transfer operation with weight from 10 to the 4th power up to 1.4 times my 10 to the 6th power n. The most critical operation to be performed by the main HROC is the precise positioning of the TC components, the interface shielding plugs, and the TCCP, the lifting system of the HROC is based on loop, each of which are connecting with the hoist. The access cell mast crane is a nuclear-grade double beam overhead crane with a telescope mast equipped with a change gripping system to allow for the connection of the different and effectors, including a parallel kinetic manipulator to manage the positioning of the target assembly, a robotic arm to manage the various RH tools for the different connection, disconnection, and inspections operations inside the TC, the interface for lifting, lowering the HFTM, and the mast grapple for vertical handling of components with masses up to 1,000 kg. Chapter 3 Conclusions. Based on the design configuration described in the previous sections, more details can be obtained from it. Is concluded that the IFMIF-DONES facility will be able to produce a neutron flux distribution with significant dose rated in the required irradiation volume. Figure 10 summarizes the capabilities of the facility. This figure depicts the available integrated irradiation volume versus the damage rate comparing the IFMIF and two different beam shapes of the IFMIF-DONES facility developed with the methodology used in 34.35. Our result also suggests that a number of topics and questions of today's science in the different activities fields of research and technology could be addressed and investigated at IFMIF-DONES without compromising its main rules as a material irradiation facility for the fusion program. These include, for example, isotope productions, nuclear and basic physics research, and electronics irradiation, among others. Considering the results obtained and the contents of the IFMIF-DONES preliminary engineering design report, the next phase of the project will be focused on the site-specific aspect as well as on a more detailed engineering design of the components and systems on the critical path to the construction phases.